So we have learned about the simple example of adding two spin angular momentum, say S1 and S2, with its own corresponding components S1Z and S2Z. And why we take this, if you add these two, you will get S1 plus S2 equal to S, and S1Z plus S2Z you get as SZ. So with you can have definitely you can define a basis for defining the two combined system, one with S1, S2 and its component S1Z and S2Z, or you can say that S1 is this much, S2 is this much, and total S and its total component SZ. Okay, so either as S1, S2, S1Z, S2Z as one of the bases, or S1, S2, SZ as the second basis. And S1 and S1Z actually lies in one subspace, S2 and S2Z lies in another subspace, and you combine these two spaces and find a total space to define or to explain the states of two such system, each with spin S1 and S2 respectively. So and you can see that while representing from one basis to another basis, or from transforming from one set of bases to another set of bases, we always have a unitary matrix, and the elements of that unitary matrix that connect one basis to another basis in the case of angular momentum representation is known as the Clebsch-Gordon coefficients. Okay, so formally, if instead of S, L, like, you just start with two spaces which are spanned by total angular momentum J1 and J2 instead of S1 and S2. So why we are considering the angular momentum states? Because you know that the angular momentum J actually have a component of L as well as S, and we say that total psi, the space psi of R actually is the orbital angular momentum. And if I just multiply with the chi state, which actually gives you plus or minus state, you will get two such space, psi plus R and psi minus two such functions, which is actually plus state with alpha. And in the position representation, you get a psi plus of R, and this is minus state with alpha, which actually gives you psi minus of R. And you can see that mod psi minus R square is the probability density, that the state is found at position R with spin minus, and psi plus of R square gives you the probability that the system is found at position R with up spin state. Okay, so with this, and you know that J is actually L and S component, and the L component, the angular momentum component, actually gives you the del square theta phi part. So naturally, plus the radial part gives you total del square, and so del square by 2m minus h cross square del square by 2m gives you the kinetic energy part, and the potential energy is simply V of R, which will be together with the L into L plus 1 by R square part of your expansion of del square. Okay, so this part actually is the angular momentum part, the angular part, and you can say that angular momentum is independent of the R. It actually depends on the rotation alone, and which means that the L square as well as H Hamiltonian, they do commute. So what does it mean? When you have certain, you solve the Schrodinger equation for H psi equal to I H cross dou psi by dou t, and what you get is a psi, and that actually corresponds to the wave function or the state functions corresponding to H. Okay, but you can see that H actually commutes with L square because of this part. H and L square do commute, and naturally spin part is independent of L. So H and J commute. H and J square operator, H and J commute, which means that angular momentum and Hamiltonian energy operator, they commute. So if you get the angular momentum states, they are nothing but they are energy states as well. So to have a easy way of understanding the different states, and if you if you have all the agent states of H or all the agent state of L square or J square, it implies that you know the agent state of energy as well. So in terms of that states, you can expand the system in any given state or of any given arbitrary state get alpha. Okay, അപ്പോൾ അതുകൊണ്ടാണ് നമ്മൾ ജെയുടെ ആംഗുലർ മൊമെൻറ്റത്തിൻ്റെ ഓപ്പറേറ്റേഴ്സിനും അതിൻ്റെ അഡിഷനും അങ്ങനെ രണ്ടെണ്ണം വന്നു കഴിഞ്ഞാൽ അതിൻ്റെ കംപ്ലീറ്റ് സ്പേസ് ഇങ്ങനെ രണ്ട് സിസ്റ്റത്തിൻ്റെ ഡിഫറെൻറ്റ് ആംഗുലർ മൊമെൻറ്റം എങ്ങനെ ആഡ് ചെയ്തിട്ട് ടോട്ടൽ ആംഗുലർ മൊമെൻറ്റം ആക്കും, അതിൻ്റെ കമ്പണൻസ് വെച്ചിട്ട് എങ്ങനെ നമ്മൾ ഒരു ബേസിസ് ഡിഫൈൻ ചെയ്യും. ആൻഡ് ബേസ്ഡ് ഓൺ ദാറ്റ് ഹൗ ക്യാൻ യു completely find or write down the expression for the state get as well as any operator in that given representation or in that given basis. ഇതാണ് നമ്മളിവിടെ നോക്കുന്നത്. And generally you start with two such system, two such angular momenta, say one with J1 and another with J2, and you can see that for any given state J1I and J1, this is the actual commutation relation you get as IH cross J1K epsilon IJK, this is known to us, and J2I with J1J is always 0. Okay, so with J1I and J2J or J2I and J1J, they always commute because they are different in their own subspaces. And J1I and J2J, they actually cyclic commutation relation. Similarly with J2I and J2J will have IH cross J2K epsilon IJK. And this, because there is no relation connecting, there is no specific commutation rules connecting operators of two different subspace. One is defined in the space of J1 and another is defined in subspace of J2 or the particle 2. Now you can see that if you have infinitesimal rotations defined in the space of subspace 1, you can write it is equal to 1 minus I J1 dot n delta phi by H cross. And if you define similarly define it in the second subspace, we know that it is 1 minus I J2 dot n delta phi divided by H cross. And if you take the product, direct product, it gives you the infinitesimal rotation operator that affects both first subspace 1 and subspace 2, and what you get is equal to 1 minus I J1 direct product with 1 plus J2 direct product with 1 into or dotted n delta phi divided by H cross. And as we know, the 1 here actually corresponds to the identity operator in subspace 2, and here it corresponds to identity operator in subspace 1, so that you have a net dimensionality for the combined space. Okay, so if I write it actually the finite angle version, if I write, you will get as d1 of r into direct product with d2 of r rotation, and what you will get is e raised to minus I J1 dot n phi by H cross product with e raised to minus I J2 dot n dot phi, and what you will get is a total angular momentum which satisfy like J equal to J1 plus J2. This is known to us. So definitely you have the component of total angular momentum is Ji. Jj will actually follow the basic commutation relation as IH cross Jk epsilon IJK, the cyclic relationship. And as a result, you can see that the J's angular momentum that actually cause the generator of J, actually the total J which is equal to J1 added with J2 actually is the generator of the rotation specified in the combined space, and the eigenvalue spectrum of J square and Jz actually follows the matrix elements which holds with J plus and J minus. Okay, that we have already learned how J, Jx, Jy, Jz forms the matrix elements in its own space of Jm. And you have now for the basis kits, we know that you have J1 square and J1 set, J2 square and J2 set, and now the combined space you have J square and J set. You can just take this total number of eigenvalues, eigenstates here, just eigenstates here, and combine them, and you will get the correspondingly J1 is the state, J1 M1 is the state corresponding to the first one, and J2 M2 corresponds to the states, and the ket of J1 J2 M1 M2 actually gives the state of combined state of these two particles, or combine these two subspaces combined to form the space. And M1 and M2, actually M1 can have values from minus J1 to plus J1, so you have 2J1 plus 1 values for M1, and M2 can have minus J2 to plus J2, and you have 2J1 for every value of M1, you have 2J2 plus 1 values for M2, and M1 can itself have values 2J1 plus 1 possible values. So a total of 2J1 plus 1 into 2J2 plus 1 possible values of set ket M1 M2 are possible. Combined state for each M1 you have 2J2 plus 1 values for M2. So and M1 itself can have values 2J1 plus 1. So total of set of all base kets you have 2J1 plus 1 multiplied by 2J2 plus 1. So this is the dimensionality. This is equal to n, and where n stands for the dimensionality of the combined space of M1 and M2. Naturally, if I take instead of the spaces of J1, J2, M1, M2, if I take, this actually gives the possible values. J1 and J2 are fixed, and M1 can assume values like that. Now, if I take instead of J1 square J2 set, J2 square J1 set, if I take J square and J set, and J1 square and J2 square, all these actually mutually commute, and hence you can define J1 and J2 will be same, so you can have J1, J2 and total J and M. Now you can see that this ket actually specifies a single state of the combined system of J1 and J2. Now here what you do is you specify them not in terms of individual components J1 set and J2 set, but in terms of the total J and the components of total J of the combined states J1 plus J2. And by one-to-one correspondence, you can see that if n is the dimensionality of one space defining the same state, same system, you should see that the dimensionality of this representation, J1, J2, Jm representation, should also be equal to n. Okay, so we know that how J1, in the combined system, J1, J2, M1, M2, you can see that if J1 square operates on the ket, you will get a J1 into J1 plus J2 H cross square is the eigenvalue. If J2 square operates, you get J2 into J2 plus 1 H cross square. Now J1 set operates, you get M1 H cross. J2 square operates, you get M2 H cross. So these are the eigenvalues corresponding to J1, J2, Jm. And if J square operates, you get J into J plus 1 H cross square. And J set operates, you get M H cross. Okay, so this is actually, you can see that J square and J1 square, it commutes. Similarly, J square and J2 square commutes. J square and J set commutes. And J1 set, J2 square commute with J1 square, definitely. And J2 square commutes with J set. J1 square also commutes with J square. J set. So all these are mutually commuting, mutually compatible observables, and that is why you define ket J1, J2, Jm as a simultaneous agent ket of J square, J set, J1 square and J2 square. Okay, so so you can see that this is one set of representation where J and M vary here. J1 and J2 are the base kets, and depending on the J1's total addition, how they add, you get J value, and depending on the J value, you have M values. And another set of representation is, actually we know that J1, J2, M1, M2, as we have seen is the individual representation, if I could say. And these two, okay, this actually corresponds to. Now you can see that there is this is actually a set of all these possible values of Jm and set of all these possible values of M1, M2. Actually this corresponds to the n. So this is the set of all agent kets can be, if normalized, can be assumed to form the basis, and this also can form the basis representing the same system. And you can see that if I can represent this ket in terms of all possible values of this ket, you can say that there could be a transformation relation connecting the ket J1, J2, Jm to set of all ket J1, J2, M1, M2. That I can represent by using the completeness property of this, like ket J1, J2, Jm is represented as sum over all possible M1, sum over all possible M2, J1, J2, M1, M2, J1, J2, M1, M2. Then you are presenting J1, J2, Jm ket. So this is the completeness of the, it's like you are representing I into J1, J2, Jm. This is I into the identity operator into J1, J2, Jm, which actually represented as this operator Jm. Now this is the element that connects M1, M2 representation to Jm representation. And this you can write as sum over M1, sum over M2, J1, J2, M1, M2, J1, J2, Jm multiplied by J1, J2, M1, M2. So this actually form a matrix, and each value for M1, M2, you have coefficients that connects representation M1, M2 with representation Jm, and this quantity, this element is actually the CG coefficients, or known as the Clebsch-Gordan coefficient. And you can see that this form, the elements of this form are unitary matrix because it transforms from one set of bases to another set of bases, unitary matrix. So now we have another property, like you have J1Z plus J2Z. Actually the Z component gives you total JZ. Okay, now equal to JZ, or you can write JZ minus J1Z minus J2Z actually gives you 0. So now what you do is you take this operator JZ minus J1Z minus J2Z operates on J1, J2, M1, M2. JZ operating on M1, M2, it's not, what you should get, it is equal to 0 itself. Now if I take you left multiply it with J1, J2, Jm, and you just operate it, you can see that JZ can left operate on this, but J1Z and J2Z can right operate on this. Okay, and what you will get is JZ operating on J1, J2, Jm actually gives you MH cross with same J1, J2, Jm, J1, J2, M1, M2, and the next one minus J1Z operate on M1, M2 will give you with minus M1 H cross and the same quantity, minus J2Z operating on this will give you minus M2 H cross, and then with the same J1, J2, Jm, J1, J2, M1, M2. Okay, so and this gives you 0. So what you will get is M H cross minus M1 H cross minus M2 H cross into J1 J2 Jm product with J1 J2 M1 M2 equal to 0. Okay. So in either case, if I start with J1 J2 Jm over here and left multiply with J1 J2 M1 M2 here, you will get the same result. Only thing that you will get this part as a complex conjugate, and you know that this elements they form a unitary matrix. So unitary matrix, the elements of a unitary matrix are like the transpose goes to the same. And if I take it as the and coefficients are all real, which means that Cij, it's unitary, and real unitary matrix is an orthogonal matrix. So Cij will be equal to Cji. They are transpose to itself. Transpose is same as itself. Okay, so it doesn't matter you write J1 J2 Jm or left multiplied with J1 J2 M1 M2 ket, or you take bra J1 J2 M1 M2 ket with J1 J2 Jm, it's going to be the same because they form elements of an orthogonal matrix. Because it has to be unitary because it connects to basis vectors and the coefficients are all real, which means that all the elements are elements of CG coefficients are elements of orthogonal matrix, real unitary matrix. Okay, so what does it mean? This is what we have obtained from the basic knowledge that we have. What you got is CGM, the coefficients, this is the CG coefficient corresponding to Jm M1 M2, and this is equal to 0 multiplied with a constant. So H cross is not a constant, so you can rewrite it as M minus M1 minus M2 into the CG coefficients, that is Jm with M1 M2 is equal to 0. So either of this should be 0 always. So when this is 0, the coefficient is 0, then this is not equal to 0. So coefficients are 0 when M minus M1 minus M2 is not 0. Or you take to the other side, you can see that M not equal to M1 plus M2. Okay, the coefficients going to be 0 when M is not equal to M1 plus M2, which means that you have non-zero value for CG coefficients only when M1 plus M2 is equal to M. This is not equal to 0 when this part is equal to 0, and that happens when M equal to M1 plus M2. So CG coefficients are not equal to 0 only when total M is equal to M1 plus M2. So this is one of the selection rules for the CG coefficients, that the total M value that connects M1, M2, Jm, the coefficients are not 0 when M1 plus M2 is equal to total M, and all other cases the coefficients are 0. Another case is with J. Now J can have value. J is actually the values corresponding to the angular values corresponding to J square, and for a given J value J1 and J2, you can see that the total J actually add up with J1 and J2, and you can see that J can have values only between J1 plus J2, which is the upper value, and with modulus of J1 minus J2. If J1 is greater, the minimum value will be J1 minus J2, and if J2 is greater, it will be J2 minus J1. So you take the difference between J1 minus J2 to J1 plus J2. Okay, so if you start counting the J values, you can see that if J2 is smaller, you will have values from minus J2, J1 plus J2, J1 plus J2 minus 1, J1 plus J2 minus 2, so on up to J1 minus J2. So it will be like 2 J2 plus 1 values for the total J if J2 is smaller, and if J1 is smaller, you will have 2 J1 plus 1 values for J. Okay, now we can see that from our convention, the total dimensionality, you got it as the possible values of m1 into possible values of m2. So that was 2j1 plus 1 values were possible for m1, and for each m1 value you had one m2, and the total possible values of m2 was 2j2 plus 1. So this was the total dimensionality of our space. Now if I represent it in terms of Jm representation, you can see that you can take values, each j value. J is from mode of j1 minus j2 to j1 plus j2, and you can see that for every j you will have m values corresponding to 2j plus 1. Okay, so you are summing over all possible values of m, and m can assume m for every j you have m equal to 2j plus 1 values, and j is varying from mode of j1 minus j2 to j1 plus j2. So if you are summing from lower value, you will get as 2 of j1 minus j2 plus 1 plus 2 into j1 minus j2 plus 1 plus 1 plus 2 into, likewise if you add up, you can see that 2j values, 2j1 plus 1 amounts from j1 plus j2 to j1 minus j2. You will get it as 2j1 plus 1. Now if I add up, you will get like minus 2j2 plus 1 minus 2j2 plus 3, so on. So you'll get it like sum over 2j1 plus up to j1 plus 2 into j1 plus j2 plus 1 plus 1. So you get upper value will be 2j1 plus j2 plus 1. So it is from minus 2j2 plus 2j2. So it will be like 2j2 plus 1. So again what you get is the dimensionality. M assumes values from 2 into j plus 1, and j itself is varying from j1 plus j2 to j1 minus j2. Or upper limit on the you will get like 2 into j1 plus j2 plus 1. So it will be 2j1 plus 2j2 plus 1. The next case you will get 2j1 plus 2j2 minus 2 plus 1. So it will be minus 2. Then 2j1 plus 2j2 minus 4. So on. It will be going, and you will get it like 2j2 plus 1 values will be there, and total, if you sum from this limit, like in statistics you learn, you will get is 2j1 plus 1 into 2j2 plus 1, which is consistent with the n values here we have obtained. So dimensionality of space should be same whether you represent in one set of bases or another set of bases. Okay, and you can see that the selection rules for j actually comes as j is always less than j1 plus j2, or less than or equal to j1 plus j2, and it is greater than or equal to mode of j1 minus j2. So the possible values of j lies from j1 minus j2 to j1 plus j2, and m is actually always equal to m1 plus m2. And you can see that the CG coefficients are unitary metrics since they transform from one set of bases to another set of bases. And you can see that all the coefficients, CG coefficients or the elements are all real. So real unitary means they are orthogonal condition, real orthogonal metrics, which means that get Jm, M1, M2, the element is similar to its complex conjugate M1, M2, Jm. The transpose are same. And you can see that the orthogonality condition from this, what you will get is sum over j, if I just write, you will get it as if you sum over all possible values of j, m, you take j1, this is 1, represent like j1, j2, m1, m2, j1, j2, jm, this is 1, then you multiply it with j1, j2, m1, j1, j2, m1 dash, m2 dash, J1, J2, Jm. Okay, so it means that you are summing over all possible values of J and M, and you take the orthogonality between M1, M2 and another value M1 dash and M2 dash. This one actually, this is one coefficient with M1, M2 and the other coefficient with M1 dash, M2 dash, and you are applying the orthogonality or the summation. This is one coefficient, this is another coefficient. Only thing is that you take the multiplication and you sum over all possible values of J and M. Okay, but you can see that this part can be rewritten like J1, J2, M1, M2, J1, J2, Jm, and this orthogonality transpose is same. So you have J1, J2, Jm, J1, J2, M1 dash, M2 dash. Okay, and this part, if you sum over all J and M, you are summing over all J, all M, which means that this is nothing but identity operator. So what you will get is J1, J2, M1, M2, J1, J2, M1 dash, M2 dash actually gives you 1 if M1 is equal to M2 and M1 dash is equal to M1 and M2 dash is equal to M2. So you can write it as del M1, M1 dash and del M2, M2 dash. Okay. So this, otherwise if they are different, they are orthogonal. Every other coefficients, they are orthogonal. J1, J2, M1, M2 and J1, J2, M1 dash, M2 dash are orthogonal to each other. They are orthonormal eigenstates. They are orthonormal to each other. So once you apply the symmetry property of orthogonal matrix, what you get is, you can rewrite it like this, and this part actually sum over all Jm values gives you the identity operator defined in space Jm, and then what you get is this, the orthogonality relation for representation M1, M2. Okay, so the CG coefficients are real as well as similarly. If I do in the other case, in the other one, if you take the second space, sum over M1, sum over M2, if I do with the same one, J1, J2, M1, M2, the same one, J1, J2, Jm, and you are summing over all possible states of M2, get J1, J2, Jm. Then J1, J2, M1, M2, the summing over all M1, M2 states, J1, J2, J dash, M dash. It's a different, these two are now different CG coefficients. Okay, and what you will get is, you sum it over all this, J1, J2, J dash, M can, or just take this, make it the other one. What you will get is J1, J2, Jm, J1, J2, J dash, M dash, and what you will get is equal to del J, J dash, del M, M dash. Okay, so this is what you get from the orthogonality, or you can say that this is a normalization condition for our get Jm. Now if I apply it over here, so what I get is J equal to J dash, this summed over M1, summed over M2, you will get it is only when J dash equal to J and M dash equal to M, you will get it is J1, J2, M1, M2 multiplied with J1, J2, Jm, and the other one is applying this del J dash, the orthogonality relation. What you will get is the same, summed over, what you will get is del, it is summed over all possible value, you get as 1 into 1. Okay, or this is 1. Okay, this is the normalization condition for our state get Jm. So this is a possible, this is not a possible one because this has to be 0, then this is possible one. So 1, 1, 0, minus 1, 1, 1, 2, minus 1 is a possible representation for CG coefficient. Otherwise, see, J1, J2 are 1, 1, it's same. J is 2, it's 1 plus 1, 2, and m can have values from -2 to +2, so -1 is possible. Now, but m is -1, so m1 plus m2 has to be -1, otherwise it doesn't exist. So if I take -1, m2 to be -1, then m1 has to be 0. So this is one CG coefficient that is selected, that obeys the selection rule to be non-zero. Okay, now we'll see how different CG coefficients are related.